Everybody hear me? I think we're good? Good. All right, so my name is Daniel Coons. My presentation here is about designing a real-world hardware abstraction layer to last. So really what the main idea for this presentation is I've seen a lot of presentations in the past that talked about designing a how, sort of the theory of it, why you do it, why it's good, but then never anything that was very practical. All right, so I was hoping to, through some project experience that I had, give some more practical tips and questions you need to ask while you're designing your how. So plug for the mobile app. It's kind of late to download it, but you can still do it if you want to rate this presentation at the end. So there's a few presentations left, so you can still get it. All right, but a little bit about me. Like I said, my name is Daniel Coons. I work for a company called TSC. We're an alliance partner located in Bloomington, Indiana. I'm a certified LabVIEW architect, certified professional instructor. Been doing LabVIEW for 10-ish years or so. And we do a lot of automated test stuff, right? And really a lot of different kind of fields and things. All right, so hardware abstraction layer. First thing kind of to understand here is, what does abstract mean? What does that word mean? So I did what all good engineers and people trying to learn things do, and I looked on Google. All right, so I got the official definition for abstract from Google here. So thing you'll notice here, it is existing in thought or as an idea, but not having a physical or concrete existence. All right, so when we're going to apply that to instrumentation, we'll look at in a minute what that means. But this idea here of not having physical existence is kind of something that's an important thing to note, kind of to start here. All right, so taking that definition of abstract, where it's this thought, this interface is how we're going to think of it. When we start applying it to hardware, really the goal as developers that we want to have is some kind of universal interface to talk to. All right, so I'm in the developer mode. I'm in this blue box here. I want to write functions that will talk to a power supply. All right, or I want to write functions that talk to a DMM. I don't care as a developer whether that power supply is a PXI 4110 or a Keysight N6700 power supply. All right, I just want to say, I need to turn the power supply on. I want the power supply on function. Okay, same for DMM or other instrumentation that you may have. So that's really sort of the stepping back biggest thing we can look at here with that hardware abstraction layer. All right, so the developers are using those high-level instrument functions, and it's a layer removed from the actual devices. So again, as test developer, I don't care. Again, even things like if the PXI is a PXI device, I don't care if this is a GPIB or serial or Ethernet device. I just want to talk to a power supply, and I want to set it to be the output enabled and that kind of thing. All right, so pros for that, again, you don't have to rely on a specific instrument model. If you need to swap this out in the future, your test code doesn't necessarily have to get updated. We can still just use those top-level power supply functions, and then we do some work behind the scenes to make our new instrument model compliant with our model here. All right, you can easily, in this type of design, also pivot between simulated and real hardware as well. So if I'm just sitting at my desk and maybe I've created some simulated versions of all these functions, it's real easy for me now to kind of swap between the two and test things out before I actually have to go to a test bench or where this thing's deployed to mess with those kind of things. And you can make these kind of updates if you do it the right way without having to recompile your executable. Right, so if you have test code or something developed and it's deployed to an executable, when you're following the principles the right way, then if I do this right and I need a new model, I don't have to recompile my whole program to get the new model working correctly. Right, now there is a little bit of a downside to using hardware abstraction layers. There could be times where it's like using a sledgehammer on a nail, right? If you have a small project just sitting on your bench, it's a quick thing. This is going to be a lot of work and overhead to have that kind of flexibility. But if you know your system can be changing, it's supported long term, then this is really kind of the thing you want to do and what you want to look at. All right, so we agree. These are good. We've heard about them. Keynote people are talking about hardware abstraction layers. You see presentations, lots of them on this track and over these technical sessions over the years. But how do you do it? K-structures? maybe. So this is sort of the older way that when I first started doing LabVIEW, this is how we did it for a lot of cases, where you have some kind of input here, some enum that's selecting what's your device. All right, so this is an Agilent DMM, I think, that comes shipped with LabVIEW. This is a built-in instrument driver example that comes with LabVIEW. So, I had this function. This is a series of things together, but this could be individual sub-VIs with individual case structures all over my code. And then when I added a new device, I'd add a new case to each of those things. And again, we actually did do this, and it was really annoying and time-consuming. So the advice is never do this. Because, one, you've lost that benefit of recompile. So now I have to add a new DMM, that's an NIDMM or something. Now I have to go and I update all of those places if I find them all, right? And get all my case structures, add new cases, add the new functions. I start running into some maybe type coercion here, as these inputs may not be the same for the Agilent DMM functions as they are for NIDMM. So now I have coercion I have to worry about, and I've gone and again I have to recompile my code and deal with all that. So this is not the way you do it, because this takes too much work. Right, so good quote here from Bill Gates. I choose a lazy person to do a hard job because a lazy person will find an easy way to do it. We want to develop software in a, quote, lazy way, and so if I have a bunch of test code again developed, say I have thousands of VIs, hundreds of VIs, I don't want to go and find case structures for every one of those functions and add new cases to them. I want to add those new drivers. I want to go and find those few functions, pick them out, and give new versions of them for my new device. All right, so that's really the big idea here. It is good software design, but it's also, you're doing it in sort of a, quote, lazy way because you're saving yourself time. All right, so looking again at this definition, abstract. It existing in thought, not having concrete existence. All right, so what we'll look at is there is kind of the abstract version of what you're talking to and the concrete version of what you're talking to. All right, so how do we do this? Not case structures. Let's start looking at object-oriented programming. So hopefully you guys are familiar enough with object-oriented programming. I'm not going to go into a lot about how it works, but just to kind of highlight what we're looking at here, the big thing with object-oriented programming is dynamic dispatch. Right, so that means it will call the specific version of whatever child class was input into the function. It will call its implementation of that function. Right, so if I have init in power supply and I give it the class of the PXI 4110, then it will call that one's init function. Right, if I give it the NIDMM class, it will call the NIDMM's implementation of it. All right, so using dynamic dispatch now, again, my test level code is only looking at these power supply functions at a high level. All right, so the parent is that abstract. All it is an interface. It does nothing on the block diagram, and I actually will show one later on, and I can pull up some examples if I need to, but the parent really does nothing. It's that abstract, no concrete existence, no real functionality. All the parent does is say, here's what the interface is, here is the inputs to this function for initialize or output enable, and the parent does nothing on the block diagram. It's where these child classes come in and they start implementing that functionality. All right, so now I have a 4110 class, PXI 4110 class that has output enable as a function, and that's where I actually do my real code. Right. So that is kind of the big idea, the quick version of what hardware abstraction layers are. All right, so we have some parent class, and this is kind of the method that I'm going to be showing here, is using it in object-oriented programming. The parent init, parent output enable for the power supply, those are the functions we want to interact with. All right, but some of what I've seen as kind of shortfalls in the discussion are here. What about complex instruments? All right, so here I have this little simple UML diagram where I have some treating of functionality here. My instrument is my kind of ultimate parent class. Every instrument kind of has these functions of init, close, create, reset, self-test. Those kind of things are maybe common to all instruments. All right, a power supply is also fairly simple. There are some things that power supplies do that are fairly common between all power supplies. Right? So again, those same functions, then turning on the output, turning off the output, configuring it to what its like current limits and those kind of things are, actually measuring data from the power supply. Right? DMMs, same kind of things. You're configuring it, setting its resolution, measuring from it. So understanding hardware abstraction at these types of instruments, fairly simple. Right? You have maybe 5 functions for a power supply, maybe 5 functions for a DMM. But what if you get into something like a spectrum analyzer or a vector network analyzer that I'll talk briefly about as well? Those are more complex, and there's going to be a lot more decisions you have to make as to what are those interface functions from my parent class. What's the abstract layer that I'm going up to make this make sense and be able to scale across different versions of those instruments if we have to swap them. All right, another question you may ask is, how do you deploy this? Okay, good. I understand it's LabVIEW classes, but how do I work on it and give it to somebody else? And how do I get this no compiling executable functionality? How do I choose the correct child class? What are the kind of steps that you're putting in some configuration file or hard coding? I'll show kind of 2 options for that as well, of how you're choosing which child class I'm using on my test bench or whatever. And then some more. All right, so that's kind of where this presentation was birthed out of, was this idea of how do you do this? What questions do you need to ask? What are the things you're thinking of? All right, so the next few slides here, what I'm kind of showing is kind of a case study of learning these lessons as we went. All right, so this is a RF test bench that I've been working on for almost 7 years now, which seems really crazy. But we wanted to follow these principles. We had seen some presentations, had started trying to do this thing ourselves using LabVIEW classes. We said, okay, this is kind of what's on this bench, right? So it's not just DMM power supply and oscilloscope or something. We have 10 power supplies, 2 power meters, a vector network analyzer, spectrum analyzer, oscilloscope, signal generator. All this stuff is on this test bench. Right? So we had to come up with that abstract version of each of those instruments. Right? So there's a lot of questions that come up when you're doing something like that. How abstract is abstract enough? What functions do we need to use that are going to be common for everybody? Then the other challenge we ran across was there's multiple manufacturers that we're using as well. Right? NI people, close your ears. National Instruments products, Keysight products, Rohde & Schwarz, Tektronix, Gigatronics. Manufacturers all do their drivers differently and all are crazy, all right? So nobody's going to be the same. Nobody's going to have the exact same functions. Nobody's going to have the same inputs. So there's a lot of things you have to look at and understand as you start to develop something that's going to be useful. And this is just a cool picture. This is not what it looked like at all, of course. Much bigger. All right, and then the other thing with this bench is, the idea was like it's 20 plus years supportable. So it's going to have to last, and we're going to be developing code on this, testing different things on this. We don't want to have to go back and update everything if you have to make a change, right? So what are some of the challenges here? The first things we're going to look at are how you deploy it. I mentioned that before. Then how do the developers know which functions to use? And there are some weird things that come up with that. All right, so that second question there, how does the user, the developer, the test developer know which functions to use? So rule number 1 is never the child. If they use child class functions, you've defeated the entire purpose of your hardware abstraction layer. You need to be using power supply functions, right? And what we saw was that would happen, right? If we're compiling code and handing it out or telling them to use these things, a test developer, our team was fairly big, so a test developer may look and say, okay, this power supply is the 4110. I found the 4110 class, and I found its functions. I'm going to use those. So some tips there. The one at the bottom with the exclamation point is code reviews are super helpful for something like this, right? You need to be able to look at someone else's code and say, you're not using the right thing. So some tips on how you do that. For choosing the specific implementation, specific concrete device or whatever, one of the things you can do is create palettes All right, so palettes you can develop. It's kind of, with pack project libraries, which I'll talk about in a second, palettes are kind of a painful process to develop that code. You have to create the palette files for every function in your library. You have to manually add them all, then you have to put them in the library, and then once you compile it, then you have to pull out the palette, and everything's good then. Right? But creating palettes is helpful because now you're giving the developer something to look at in LabVIEW that they're used to. Right-clicking, they can go to instrument subpalette or PNA subpalette, spectrum analyzer subpalette, and now I can select those functions. And if they use this, I know they're pointing to the parent class. Right? Another thing that we found really useful is use colors to your advantage. So I'll show in a minute here, you can kind of see it in this palette here. We made all the parent classes, except for Switch. I don't know what happened there. Somebody went rogue, but they all have a blue banner on them, right? So what we did with child classes was we put red banners on them. So that made code review super simple, as I could walk up to somebody's desk and say, I see red, you're not doing the right thing, right? Something got mixed here. So colors for banners, for functions, really useful for this kind of thing, right? And then the other thing I mentioned, deploying, again, kind of pack libraries is the way to go. If you want to not have to recompile your executable, you're going to have to be using pack libraries for this, right? So that, and we'll look at some strategies for this as well, but the pack library then says, okay, here is your code, it's non-editable. Now they can look and pull out the functions that they need, they can get the parent class that they need or whatever they need to do and start passing that code around. All right, so pack project libraries, I'm not going to go into a whole lot of detail about how they work, but that is kind of the methodology that you should be using kind of to deploy this to people. And again, what they provide is it's like a compiled LabVIEW library, so it can't be edited, but we can create these palettes and make sure everybody's pointing to the right thing. All right, so a couple things that come up here are, again, how do you do this? Okay, I get it. Classes, libraries, pack project libraries, those kind of things. So I'll show two different kind of methods here for setting up a project to do this kind of thing. The first one is what I call kind of an all-in-one project. All right, so the parent and the child classes are all in the same library, which I'll show on the next slide as well. So parent class is there, child class is there. I build them kind of all together. What this allows me to do is easily hide child classes. So I can set a pack project in the library, I can set an entire class to be private. So when I deploy it as a pack project library, it doesn't even show up as an option. Because again, we ran into that kind of a problem as well. When the developer saw the pack project library for power supply, they saw they needed to be using the 4110, they would pull those functions out, right? So this method, I can hide those from the developer. So they don't even see that, all they see is those top level functions. The way that you choose your child class, which is again something we talked about, how do you make sure you're choosing the right child class, is by doing something like hard coding it in here, right? So this method is called create. Every instrument type that we have has a create, and create essentially starts the session to this instrument. It tells me which child class I'm using based on a reference designator input, and then I can start controlling the instrument, right? So if I know this test is controlling DMM1, it's going to come in here and pick the NIDMM, cast it to a generic DMM type, and then now they're using those DMM functions. All right, and once dynamic dispatch happens, when this thing runs, then it will choose the right NIDMM override functions and start doing that code specifically for the NIDMM. All right, now there's downsides to this. Obviously, you have to save the library with every new child class. So you are recompiling your instrument itself. The DMM has to be recompiled whenever you add a new child class. And any instrument change you make as well. So if I discover, oh, okay, my NIDMM implementation of configuration doesn't work, I'm going to have to go and rebuild the whole DMM. Okay. They're fairly small file sizes unless you use Rohde and Schwartz, whose drivers are like multiple megs. So every time you build one, the pack library is also multiple megs. So it's not too big of a deal, but you do lose some of that flexibility, right? So, and again, like the idea of hard coding is probably not great in a lot of cases because you do have to go back and update this. Now, what you do save is your test code still doesn't have to be updated, still doesn't have to be recompiled in your executable. You can still point to this new pack project library and get the new functionality. Everything's good there. But your project has to kind of track all that stuff, right? And what it may look like is something like this. So I have my AllinOne Project HAL here. Maybe hard to see in the back, but I have a DMM library, which has DMM parent class, NIDMM child class. So again, the parent is abstract, the child is concrete functionality. I have build specifications for each of my instruments here. Again, I have a power supply, I have a VNA. I can build my DMM, I can build my power supply, I can build my VNA. I could separate each of those into projects if I wanted, but I can keep them all kind of together. And one reason you might do something like this, I said there are, again, there are some downsides like hard coding and those kind of problems. But if you know that you're supporting a bench that's not going to be changing a whole lot, and that a change to an instrument is a big deal, there's going to be a lot of process involved in that kind of thing, right? So my customer is specifically a Department of Defense customer. If you change anything, there's paperwork for months, right? So it's a big deal to change an instrument. So for us, resaving this thing and rebuilding the entire DMM is kind of small in the grand scheme of things, right? But what we see here, a couple examples. My pack library DMM that gets built, I've marked my NIDMM child class, the concrete implementation, as private. So once my compiled pack library comes out here, you see the DMM functions and only the DMM functions. You don't even see the NIDMM inside of this pack library. So the developer now does not have any temptation to accidentally grab the wrong functionality, right? And then I was kind of showing here, here's what the front panels may look like, the icons look like for these two different versions, right? So my parent, my DMM initialize function has this blue banner on it. My NIDMM has the red banner. Again, that's awesome for code reviews because it's real quick. I can look at somebody's code, even if you have to just print it off and give it to each other or send it as HTML documentation. You can really easily look at this and see it and say, okay, that's the wrong function. So something went wrong there. They misinterpreted something somehow. All right. Now, a more software engineering approved best principles way to do this is to use more of a separated method. All right. So the way this thing kind of works is every model, every instrument type exists in its own project and its own library. Right? So all models in individual libraries, the parent is only defining the interface again. So I have all my DMM functions. I have all the inputs for those functions and what they are. I build that. Once I've built that, then the children inherit from my deployed abstract parent. And so there's another weird little tweak here that you have to do. So in my project, you can see from my NIDMM, I have a pack library for DMM. I have a pack library for instrument, which is like my grandparent class. And my settings for NIDMM, I set the inheritance to DMM class in the pack library. All right, so I'm pointing to that abstract parent that's already deployed and built. All right, so then I can build a new child class without the parent having to be rebuilt. That's kind of the big idea here. So now DMM always exists, never has changed. When I need to add a new DMM, I just add a new project, inherit from the right thing, build it, everything's good to go. You can even set up scripting to set up some of this project stuff for you, or define like a generic project and just save as. So it's pretty easy to create those projects. There's things you can do to save yourself time. But again, one of the downsides here is it's a lot more projects and libraries you have to maintain. Right? So any DMM type, any VNA type that I may have, I have a project for it, I have a library for it. So it's just a lot more code that I have to maintain and exist and rebuild everything. If I have to go and change one of the DMM functions, I have to go in every one of those child classes and change kind of the interface for them as well. Right? So everything has to match up there. And then how we're going to choose the child class in this case is by using some kind of configuration file. All right, so now again, we're a lot more flexible because I don't have to hard code that thing inside of there. I can use a configuration file and I can update it, and then my packed libraries are still all good to go, and I load in the right thing, and then I'm running along the way. All right, so what that will look like, again, is a function here that I've called create. And basically what I'm doing here is I'm giving a reference designator to some VI that is going to look at a configuration file. It's going to give me something like the Visa resource name, potentially for this specific reference designator. It's going to give me what the model is that I'm looking at, and I'm going to load up the model and put it onto my object that gets passed along. Right? So now my wire is NIDMM or whatever I've set my configuration file to. Okay. So then I can write some of these common functionality here, initialize the instrument. Now I'm talking to it when I use create, and then I'm good to go. And I'm, again, looking at that configuration file every time I start talking to the DMM. So I could potentially change DMMs while I'm testing for some reason. I don't know why you would do that, but you may be able to do something like that as well. All right. Okay, so going back to challenges. There are some things that are going to come up for you that are questions that you're going to have to ask, all right? And so I do have a list of questions at the end that you ask that I don't have, there's no silver bullet answers to. But so one of the things here is, what functions do you create drivers for? Okay, and what inputs do you use? So again, if I'm looking at multiple manufacturers, I have Rohde and Schwartz device, I have a Tektronix device. Rohde and Schwartz has these 8,000 functions that I can do. Tektronix may only have some subset of those things. All right, what do I use? What do I pull out? Another thing you'll run into is a lot of OEM drivers. If I just want to set, say, a power supply, if I just want to set some kind of overcurrent protection, the function to do that from manufacturer 1 may also contain 3 other commands that are inside of there. All right, so what do you do about those kind of things? So one thing you can do is learn from the mistakes of others, like me. Again, this was a development we started 7 years ago, so there's been a lot of lessons learned over time. So the first thing I'm going to look at here, some points that we can get on the same page about. VNAs are complicated. If anyone does any RF testing and has used a VNA, they are complicated beasts. But once you learn how to set them up, do that kind of thing, they're fairly straightforward. A lot of the functions are basically the same. You just have to learn the quirks of the instrument. And a lot of OEM's drivers are very quirky in how they work. Right? You are looking at remotely controlling an instrument that has thousands of functions that it can do, lots of capability that it has. So you may run into some weird things like this. All right? So this was a big thing that we looked at. It's taking a measurement from a VNA. All right, so one thing that was weird about the VNA that we had, there was kind of several points here. If I want to create a measurement, here are the steps that I have to follow. I have to create a trace after I make sure that it doesn't exist, and I have to name that trace. I then have to create a measurement parameter, and I have to make sure that measurement parameter didn't exist before or will throw an error. If it did, I have to delete it, and I have to give it a name as well. Then I have to select measurement type. All right, so now I'm choosing what the type is. And that's, if you're familiar with VNAs, something like S21, or after that, gain, group delay, those kind of things that you can do, VisWAR. Then after I do that, I take my measurement channel and I apply my measurement channel, that parameter that I'm measuring. I apply that measurement channel to a trace, and then I apply that trace to the screen. All right? And each one of those things, for some reason, has a unique string name that it expected. And again, we had to check for every one of those things. Does this parameter exist? No. Okay, create it. Does it exist? Yes. Delete it, then recreate it. So we were doing all these steps, and we had functions for every one of those things. All right, so we had to have the developer track the name of the trace, the name of the channel, the name of the measurement parameter as they were developing their code, because whenever we went to measure, they had to pass all that information in, which seems like a really silly thing to do, and you're probably standing there saying that's really silly, and that's what we learned. So one of the things that was also weird was that the channel didn't equal the trace number on the screen. So we were calling everything channel 1, but it would sometimes be trace 4 or trace 5. Just a weird quirk. I don't know exactly what's going on there. So we started to ask the question, finally at some point, we had the idea, do all VNAs act this way? Is it just ours? This seems really weird and like a huge headache. Why are we making the developers track this name constantly? Because we kept running into these integration problems where we try to test something, somebody didn't use their shift register correctly to keep track of that name, and they would get the wrong parameter and throw these values all out of whack and get all these errors and didn't know what was going on. So what we then did was say, let's keep those minor details behind the scenes, right? So instead of doing all that stuff and making a driver or a parent VNA function for create channel, create parameter, create trace, apply channel to trace, all those things, we said, let's make two functions here. Trace setup, where we give it those inputs. What's our trace number, channel number? Those are just inputs into this thing as a cluster. Here's my measurement type. And then behind the scenes, genius idea, we tracked all that information ourselves, right? We're using an object. We can keep track of those string names on the object, okay? So I create trace 1. I can really call it anything I want. So we were just saying, okay, it's measurement parameter 1, and whenever they looked at trace 1 again and came to measure, I tell it what my trace was, and then behind the scenes, it looks at those strings, pulls out the right thing, right? And again, where that's beneficial is there's another VNA that we may get that probably doesn't do it in this weird way. Maybe this is just the quirk of ours. So now we've kind of abstracted all that detail out from the user, and now we're pulling up at a kind of higher level here. So now instead of these weird functions that they have to track, I just set it up. Now I can measure, right? That makes a whole lot more sense than doing all those other things. Okay, another weird thing with VNAs, or I guess maybe not a weird thing, but how they work is you can use electronic calibration modules, right? So again, if any of you are familiar with VNAs, a lot of what you have to do for cable normalization, so you have to have a short, load, opens, and throughs, and you have to have these little mechanical standards, and you hook things up, and you take these measurements to get path loss and BizWar compensation and all that kind of stuff. All right, but an ecal module kind of allows you to abstract some of that. It's a little device that is essentially like a calibration standard for all of those things kind of built in. Right? But to make sure that that thing is measuring correctly and giving you your normalization, you have to do what's called characterizing the ecal module. Right? So I have to understand what the ecal module looks like before I can apply normalization. And really, the whole goal of all this stuff is just to say this cable is this long and what's that doing to my measurement, right? But there's a lot of weirdness that you have to do for something like that with a VNA. All right, so characterization requires a lot of descriptive inputs. So they are in this cluster right here. So the cal set has some kind of name. We have to describe what our connectors are on the port. We have to give some kind of user description. These are just text field port description as well. All right, so all that stuff is input. If you look at the programming guide for this VNA, all of those things have individual functions as well. So what did we do as first step? Let's make VIs for each of those individual functions. So for some reason we had a ecal characterization user description function. We had an ecal characterization port 1 connector description. All these VIs that we're creating and tracking. All right, so we created a function for each one of those things, did our overriding magic with our VNA that we were using and implemented the code. But then we found ourselves using all of those functions every time we performed a characterization. All right, so anytime we did an ecal characterization in a new UUT, we would essentially we just go to the old one and say this one worked before, let's copy out these 20 functions and let's put them in here and do it again in this new UUT code. All right, so we were copying over and over and over again. And then we had this genius idea to make a utility, that the utility included all those functions in it. And we had an even better idea and said, why are we even doing that? Why do we have a utility that is combining functions together when you could just combine those functions together in a function for the VNA? Because that is what we were doing, right? We are setting up an ecal and characterizing it. All right, so a better approach was we are pulling those functions up. And this is the principle of encapsulation. Now, instead of saying set the user description, set the port connector type, set all these things, instead of having individual VNA functions for those, we then went to a method where we had a VI called eCalCharacterize. Right, so what you see, the front panel of that is here. So it has this cluster input of what those inputs are. Right, again, these are going to be input every time, so it makes sense that they're there. But again, this kind of shows what the abstract parent does is nothing inside of here. All right, my block diagram literally has nothing in it aside from a pop-up that says if the child class did not implement this function, it's basically a warning for development time to tell them that they need to do something about it. Right? There's other ways you can handle this type of behavior as well. If you know that user has to implement every one of the functions, you just make it a required override, and if they don't override it in their class, then their class is broken. But we found that this was a good way too, that if somebody was just trying out something new, it's just a quick pop-up that they see that says, okay, we didn't do something right. All right, so again, parent is abstract. We're looking at the block diagram for eCalCharacterize. It does nothing at all if it gets called, which is why you need a concrete implementation of it. Right, so this is what the child class looks like, and it does have a couple extra functions inside of here, so I'll show you the next slide and you'll understand why. But we did eCalCharacterization Setup, which is all that beginning stuff. Then we say perform the thing and then look for an error, right? So before, we had, drivers for, we had individual drivers for everything like this before. So this is what eCalCharacterization Setup looks like now. Instead of making a function for each one of these things, which would be crazy, it's just doing them all in line here. Right? So I'm sending the specific message to set IDs here of the ecal module, and on and on. This one's kind of long, so I couldn't fit it all on the screen. But this is basically pulling that information from the programming guide, figuring out what those specific Skippy commands are to set these things, and then setting it kind of all in one fell swoop, rather than individual drivers. All right, and again, what you're looking at here is the idea of when I go to make a new UUT, or if I have to switch this VNA out or this spectrum analyzer out, is it going to do things the same way? Maybe not, right? But having just an eCalCharacterize, I know that's a function that I'm going to have to do no matter what I have. Okay, so I pull that and say, this is one function, these are the general inputs, let's handle all that other crazy stuff behind the scenes. All right, so what if you get down to a change that may have a big effect? All right, so our test bench was originally set up to test 3 UUTs. That was kind of the goal of what we started with. Those 3 are done now. 2 more are completed. There's like 6 more in development. All right, so this thing from successes has grown and grown and grown. We did not, we were designing with that idea in mind, but the original goal was just 3 things. So if I had to update those 3 things, maybe not a huge impact, but now that we have 10 or 12 in development, again, thankfully we followed some of these principles, and now if we have to fix something, it's a little less impact. Now, there may be functions, like we discovered here with configure channel enable for a power meter. As we started, we actually have 3 or 4 different types of power meters now from different manufacturers. We, I think, originally created this function based on IVI. So we looked at an IVI driver and it had this thing and claimed that it did something. And we found that every child class we were making basically said channel enable does nothing. Right? There is no such thing as enabling a channel on a power meter. Who knew? Okay, so what we decided was, because we've already got a bunch of stuff signed off and out there in use, okay, we'll just kind of deprecate this function. We took a page kind of out of NI's book, so if anybody's familiar with write to spreadsheet file and read from spreadsheet file, you can no longer find these things because they've been replaced. And if you take LabVIEW courses that still have them in there, they will have this giant red X on them, as you will see. So it says in here, LabVIEW no longer supports this function, blah, blah, blah. It's just left for backwards compatibility. All right, so we kind of did a similar thing here. We put in some documentation that said, hey, this doesn't do anything. You can use it, but it does nothing. And then even saying it doesn't provide a beneficial function. That's good word work there. And then we kind of marked this thing out. The other thing we did was we took it out of the palette. All right? If they shouldn't use it, there's no need for it. It doesn't really do anything. Just take it out of the palette. You can kind of hang on to it as time goes so that those other things don't have to be updated. But we're kind of documenting for future developments. You don't need this thing anymore. All right? So, and again, it was several of those TPSs or UUTs that we already developed code for that were signed off. We kind of, that trade-off of do we go back and update them every time, and we found it was every time we were using the power meter, we were literally like creating it, enabling the channel and doing XYZ. We were like, we're going to have to go back and kill all those things. Okay. Or just do this kind of thing and say, let's leave the function there, it's deprecated, everything's good to go. All right. So, some of the important things that you may need to ask, and again, I'm going to give a list of questions here, which are kind of things to think about as you go back and start implementing this, because again, a lot of the presentations are just, hey, this is great, see you later, have fun. There are some things you have to think about that there's really no silver bullet answer to. There is no, I was in a session earlier this week kind of talking about, is there a hardware abstraction layer to rule them all? And there really isn't. I don't know, maybe there's somebody else that has a magical solution, but there are going to be things that are specific or whatever to your project. All right, so first question, how generic / specific should I get? Okay, so this is things like that VNA measure. VNA measure took several steps. Should I just bring that up and say, okay, we're taking a measurement. That's really the big idea of what we're doing. Okay, do I need a function for creating a measurement parameter that really does nothing for the computer? It's just does nothing for the VNA or the measurement, really. It's just kind of how it has to be done for this specific instrument. Will the next one have that kind of thing? So thinking of like what is high level enough that a new replacement instrument will do the same thing. And again, if you're using power supplies, you're using DMMs, hopefully this is very simple. Output enable is going to be in every power supply, so you got that one taken care of. All right. Have I looked at multiple potential instruments to see commonality? So one thing that may be useful, at some point somebody decided on this VNA or spectrum analyzer that we have, right? There were probably things they were comparing against. So going and looking at those comparison models may be useful, their drivers, their functionality, how they do things, to understand, okay, if we had to switch to this other OEM's driver, would ours still be compatible? All right, so that's a big question there. All right, am I designing around need or how the OEM driver is set up? Again, this is kind of understanding what are we going to be testing? What are those high-level functions we need? And again, what we need. Or are we just looking at OEM driver setup? A lot of what we fell into, those problems early on were, okay, we have this VNA model. This is how its driver set does it. The OEM driver we got from the instrument driver network. That's how it did it. Let's create all the same functions. And then found all the headaches in doing something like that. Some of them, like I said, we designed around IVI when we started. Some of them, again, we were looking at, if you've ever used, I'm not trying to rag on Rodian Schwartz, but if you've ever used Rodian Schwartz, their drivers are crazy. There are functions to do literally anything ever for every option that could ever be on the instrument you have. So do you need to create all those functions? Probably not. Look at what you have as your needs and your measurements that you need to do. All right. What about the inputs? So are the inputs for this function common across different models? That kind of thing. Again, you may run into a situation where I'm looking at an OEM driver that does overcurrent protection or something. I think I'm going to talk about this. If I want to only set overcurrent protection for my power supply, maybe in OEM driver 1, it has configure, which sets overcurrent protection, overvoltage protection, and something else inside of it. Right? If I only want to set overcurrent protection typically the recommendation we did was never, ever update those OEM drivers as step one, because you want to be able to give that to somebody to download themselves, right? What we did instead was pull out from that OEM driver, if they claim that it worked, let's pull out the functions we need and put them in our own VIs. Right, so that's actually what you saw from that ecal characterize ugly thing child implementation of that function early on, was we pulled out the guts of that OEM driver and we pulled out those functions we needed. Right? And then do we need all the inputs this driver has? So again, some driver functions that you'll see from OEM palettes and things have lots and lots of inputs that maybe aren't useful to you, right? Maybe for configuring a DMM, all you need is resolution and units, but there's 6 other inputs on there for some reason. Again, probably extra functionality that is probably not something you're ever going to use, right? What we have kind of learned, you know, there's still a trade-off to that. Maybe you do need some of those things kind of on down the line. Really, the recommendation there, you can add a new function. Okay, it's going to be a lot less painful to add a new function that has those other things in it than it is to try to implement it for something that can't actually do that. Right? More questions to ask? Do we need a completely plug-inable solution with separate projects for everything, or is kind of that all-in-one idea sufficient for us? Right, so those 2 approaches I said, you know, generally kind of software engineering best practices is to use the separate projects, the separated method of those functions. But in some cases, again, like I said, even for our test bench, we did kind of the all-in-one approach because we knew that if we ever replaced something, it was going to be for some major reason, and that major reason was going to give us time to do lots of development anyway, so it wasn't that big of a deal, right? But I've also worked on other projects where we're trying to make it more generic and more plug-inable, so in that case, you need to do kind of the separate model, right? And again, is the way this measurement is implemented common or specific to this model only? So again, thinking like this VNA idea, VNA measure, and setting up that trace. Do I need to do 50 steps to do that and have individual functions for it? Or is the next one literally going to be awesome and combine all that for me and just say, I want to do this measurement, and the driver does the same thing? All right, so it really comes down to kind of understanding what you need to do at a high level. And then, if I have to make a change, how big of an impact is it going to be? So that's where you get back to kind of that idea of deprecation. If I get rid of, or if I add a new input to this function, and now I may have a problem here if I've added a new input that the other old things I developed are not going to have or need, is that going to have an impact on my code? In some cases, if you do something like that, it may actually break your executable all of a sudden. And executables in LabVIEW, if you've ever had them crash, do not give you any helpful information whatsoever. It is literally open, closed. So a lot of times I've found that's something like pack libraries where it's expecting it to have this specific interface, and maybe I went and mucked something up, and now it doesn't really understand how to load that anymore. So really understanding the potential impact of those changes is really important. You know, one thing we were trying to do at one point is kind of map out, finding a good way to map out, like if I change configure channel enable for the power meter, how many tests is that going to impact, all right? Is there an easy way to tell that it's going to impact these 20 things that I need to regression test? That's probably a good thing to try to track because, again, if you make changes to that implementation, you're going to have to regression test, or if you add a new instrument type, you're going to have to regression test, those kind of things. Right, so I need to know what uses the power meter or what uses specific functions like that. Right? So again, a lot of these questions we have been refining and learning over the years of this development. Like I said, it's kind of a at this point, 7 years kind of ongoing thing. So it's good to think about these things ahead of time, but also good to tell yourself that you're not going to get it exactly right the first time. Right? There's going to be times and revisions and those kind of things that you're going to have to do. There's no real silver bullet to this type of thing. Right? So really what you want to understand is if I have to be updating for 50 UUTs, have I designed this in a way that's going to be kind of scalable so I don't have to go literally in 10,000 VIs and update little case structures or something like that everywhere. All right, and that is kind of the end of what I have. Does anybody have any questions? Yes.
Do you use the same HEL for more than one project?
So recently we found ourselves kind of redesigning a similar thing over and over again. So we've been working on kind of a generic how to rule them all in some ways of trying to find those common functions. But yeah.
Do these different projects have different classes of test equipment in them?
Yeah, I mean, some of them have a subset. Like this one, I think was really an awesome one to start with because of the list of how many things were in there. I mean, it was so long that it was really useful. But yeah, we've been kind of looking at how do you pull out, if I had this project is just power supplies, then I can just pull out the power supply libraries or whatever. And that's where that kind of separated project method is a little better or something like that.
Could it also be more performant if you're not, if you're loading a pet project library, a large one versus several small ones?
Potentially, yeah. They're fairly small, to be honest. I mean, it doesn't. The largest one we have is probably a couple megs, and it's again because of all the help files that come with it from a driver. But yeah, it's probably somewhat faster to. It could be somewhat faster to load it, having it hard-coded, than it is to dynamically load it. But I would say the impact is so minimal that you wouldn't know. Is there another question? Yeah.
So one problem that comes up for me sometimes is that we'll have a specific instrument that will cover like 95% of our use cases, and then we have maybe a more expensive instrument that we only need some of the time, but it's because it includes some maybe more advanced feature that the cheaper one can't do. And it's always kind of tricky to figure out how to have a hardware abstraction layer where sometimes you can do this thing and sometimes you can't.
Yeah, I mean, is the 5% extra instrument you're getting only doing those functions for that thing?
Right, maybe one of the benches has it and all of the rest of the benches have the cheaper one.
I see what you're saying. Yeah, for something like that, you'd almost have to, I don't know, you'd have to have some kind of configuration to say, like, this needs to be up front, this needs to be tested on the bench with the higher capability, if that makes any sense. Like, one of the things we do typically for like a UUT, we have a configuration file for it that says, here's all the instruments it touches. And the first thing it does is says, are all of those instruments in cal? If they're not, then it gets a warning to the user saying, hey, we're going to mark this data sheet that this isn't valid. But if everything that say a DMM is not in cal, but I'm not using it, then I don't care about it. So similar idea, you could do like, okay, this UUT I'm testing needs this specific functionality. Does it exist on this bench? Maybe goes to look at some other configuration that would do something like that. Say, no, you have to go elsewhere, that kind of thing. That's probably how I would handle something like that. Yep.
Are you familiar with agile design principles?
With the what?
Agile design principles.
Child design?
Agile.
Oh, agile, yes.
Yes?
It's not to the extent that you are, but very minor level, yes.
Did you read the books?
No. I can't.
If you had, it would save you 5 years out of 7. Because I really like your presentation. I was carefully listening and trying to figure out whether you would step the fine line of making mistakes, and you didn't. You did everything right, but you're using different notions than the software engineers and the language in the book. And some of the problems you would face, or you kind of listed in your question list at the end, you could solve them if you knew those principles up front.
Yeah. When I was
this
going
is
over
really
this with John,
presentation from software engineering standpoint.
Yeah, John was telling me to throw in some terminology when I was. But,
Yeah, and I have an example for a scanning microscope, which really nicely maps into your test station.
Yeah.
You can substitute one for another.
But no, I can't read the book. It would put me to sleep. I've tried, but It's hard. It's hard for me.
Skip the C++ example.
that too. Any other questions? All right. Thank you, everybody. Thanks,
Yep. Yeah.